Already?
So I think we have 45 minutes left. It's possible, but
okay. Have you got any questions for the first one already? At what height above ground?
Yeah, normally, let's say 10 meters.
10 meters above ground,
Yeah.
5 meters per second is a very, very, very good wind site.
Yeah,
It's an extremely good wind site.
Yeah, because actually this area is very open, coming from Australia.
Yeah.
Yeah, this is very open. That's why I said to you that this around this wind speed.
Okay.
Yeah.
Okay, because 5 meters if you've got open sea, the roughness length is quite low.
Yeah.
So the increase with height is not that much. But anyway, if you start, if you've got at 10 meters height, if you've got 5 meters per second, at 30 meter height, you probably got 7 meters per second, or 6.5.
Yeah.
Which is an extremely good wind site. If you then go to 50 meters, you probably get up to 7.5, which is comparable to the best wind sites we've got here in Germany. All right, but if you say you've got 3 meters per second at 50 meter height, then forget it. But if you say you've got 3 meters at 2 meter height, then that might be reasonable.
the NASA report says 3 meter and 10 meter height.
Yeah, okay. Well, NASA is not too reliable actually in this regard.
Okay.
But yeah, usually, well, I can, this is actually also one of the products of my company. I just got 2 flyers actually, but maybe you just want to share. I just have got 2, unfortunately. So this is a product of my company, Compact Wind Monitoring Systems. It comes in like a suitcase, yeah? A box, can be shipped by air freight, and there's everything in there, like the tower for wind monitoring, anemometers, data logger, power supply of the data logger comes from photovoltaics integrated in there, batteries integrated in there. It stores the data on an SD storage card. So this is actually something for low cost and high quality wind monitoring campaigns. And as I said, like, you probably do not want to rely on NASA data because that can be 100 or 50% wrong. And they even say on their own website, be careful with the wind monitoring data because that is just measured from satellites with air movement, and they measure at 50 meters height.
100 maybe.
Yeah, at 100 meters height, and then they extrapolate down to the ground, and therefore it can be completely wrong at 10 meters height.
Not on site.
Yeah. So, and this is what you set up if you want to set up small wind turbines, hybrid power systems.
Actually, we have the wind turbine small, yeah, only 500 watts.
500 watts, yeah.
But never.
Yeah, of course, because the location is very. We have a lot of tree there, no wind, and also building.
Yeah.
I was thinking about it.
Yeah. Okay. All right. Well, any other questions? Okay, wind speeds they always want to know about height. Where is it measured?
Yeah.
As I said, 5 meters at 10 meters, like 5 meters per second at 10 meter height is a very good wind site. 5 meters per second at 50 meter height is a bad wind site. And it's usually like the indications are usually between 10 and 50 meters. Like usually you have either 50 meters indication, 30 meters indications, or 10 meter indications. Okay, let's go into the resource, wind resource, a little bit more. If you have got a very windy site, you can usually already see from the vegetation, like on the picture on the right. But this is definitely a good wind site.
Natural sign.
Yeah, natural sign. All right, and now, as I said, turbulence. Turbulence. What is turbulence? Turbulence has got these 2 components, and one of the components can be calculated at this. Turbulence intensity I is the standard deviation of the wind speed divided by the average wind speed. So this is how you can make the eye independent of the actual wind speed. And you can get a value for a certain site. Yeah, standard deviation of wind speed divided by average wind speed. Turbulence comes from obstacles in the surrounding. Bushes, houses, whatever, cars, rocks. And just as a rule of thumb, you're safe. You're definitely outside of the turbulence area if you are twice with your rotor, if you are twice as high as the highest obstacle in the surrounding, then you're outside of the turbulence area. Otherwise, you cannot, like nobody, even experts, aerodynamic experts, they cannot estimate turbulence areas by just looking at them. There's another rule of thumb. Turbulence areas are 10 to 15 times behind an obstacle, like 10 to 15 times the height of the obstacle behind the obstacle. And there's also a turbulence effect in front of this obstacle of 5 times. Just as a rule of thumb. Okay, this is what we've been talking about already. Here are some roughness length. And this is also very interesting, the energy index, just as to give you an idea. If you've got water surface, as you said, you've got a very low roughness length, you've got 100% of energy coming from the wind. Now, if you have like more roughness length, you can get down from 100% of energy due to turbulence down to 18% of energy, just because there is more turbulence in that area. Same wind speeds, but just more turbulence. And this is the formula you use to calculate using the roughness length from one height to the other. You probably know that, don't you?
Yeah.
You know that formula. Okay, wind data assessment. You get this kind of data from your data logger, and then you can derive Weibull functions from that, which look like this, for example. A usual Weibull function for a wind site is the function with k equals 2. If you don't have any wind data really available, you just have an average wind speed, then you take the k equals 2 curve to estimate your energy yields. And that is called Rayleigh distribution. Like if you have a Weibull distribution with k equals 2, then this is the Rayleigh distribution. This is again the change of wind speed with height. This is some information about wind monitoring. This is also what we do sometimes, large wind monitoring. So you've got a mast, you've got a tilt-up tower, GIMPO. You connect the measuring system. So actually, this, you see, this is quite complex, quite a big box. In this unit, the data logger is just like that, and it integrates all of that electronic on one circuit board, more or less. And then you have a grip hoist, for example, to pull the whole thing up. So this is, I think, this is a 60-meter tower. Sensors, calibrated sensors. So this is actually the wind monitoring system, as you've got it on your flyer.
Every seconds you can.
We measure every 5 seconds, and then you can select the averaging periods. You can select either you record 5-second steps, then you have like a data set which cannot be handled by, for example, Excel easily anymore. You need any other additional tool for that. Or you let the data logger compress the data more or less in terms of building averages of 10 minutes, 15 minutes, 30 minutes, or 1 minute even. Yeah, 1 minute, 5 minutes, depending on what you need. Yeah, right. So, and this is an example for a wind data evaluation. So you get the wind data for example, 2 anemometers. The blue one is the top anemometer. You see that this has got the higher wind speeds, and this is a graph showing the percentage of time at which a certain wind speed occurred. So for example here, between 3 and 4 meters per second, we had at the top anemometer, we had some 26% of the time, we had 3 to 4 meters per second. And at the bottom anemometer, we had approximately 20% of the time we had this wind speed. So this is how you can walk through all of the columns.
So normally we put this anemometer at the hub.
Yeah.
Right?
That would be advisable, but it always depends on your budget, actually. If you can afford a tower high enough to measure at hub height. If you don't have that budget, you can still measure below and extrapolate to a different height with a logarithmic formula.
How is the accuracy when we do
The extrapolation. If you've got several measurements, like 2 or 3 or 4 or even more measurements below, you get a pretty good idea about the roughness length. And then if you, for example, if you've measured up to 30 meters and your hub height is 40 meters, that is very reasonable, can be done. Like these towers we have here are 10 and 15. So we say, okay, if you go up to 18 meters and you don't have any like obstacles in the surrounding that are higher than 7, 8 meters, then you're well off. You can extrapolate to 18 or even to 20 meters. But if you, some of our customers want to measure at 15 meters and want to extrapolate to 40 meters, and that doesn't make sense anymore. Yeah, and then of course you can extrapolate to other heights, and you see, okay, the wind speed, average wind speed gets more. At most wind sites throughout the world, you have quite a strong daily wind pattern. And I would assume that in most of your islands, you also have a very strong daily wind pattern because of the land sea breeze.
Yeah, but depend on the location, because actually in Indonesia, at the north of Indonesia, I mean, it's very, very low speed.
Yeah.
But at the south and west,
Yeah, but even in the low wind speed areas, you've probably a few hours of the day which are quite constant, where you have a little bit more, and a few hours of the day where it's less. And that is usually due to the land sea breeze, like the temperature differences between land and sea, and then sometimes it goes around like that, and sometimes it goes around like that. Yeah, then you can analyze the wind direction in terms of the average wind speeds coming from different wind directions and the percentage of time the wind came from a certain direction. And from this information you can derive which of the obstacles in the vicinity have which effect on the rotor and the wind turbine. And this should also be analyzed. If you do not analyze that, you might put the wind turbine at the wrong spot. Well, yeah, and the calculation of the electricity cost is at the end the annuity of the total expenditure divided by the energy yield per year. And the energy yield per year is calculated like this. This is the columns of the wind speed as measured with the measuring device. This is the power curve of the wind turbine. If you have a store wind turbine, you have got like this, yeah, like this we saw before, like this. And if you multiply each of the columns with each other, you get a row of columns like this. And if you add up the kilowatt hours of each of the columns, you have got the energy, the annual energy yields. Like, let's say, okay, maybe once more. Okay, so for example, here you see this is 6% of the time we had 8 meters per second. These 8 meters per second, at 8 meters per second, you get some 10 kilowatts of power from your wind turbine. Then you say 6% into 8,760 hours per year is that many hours per year. Into 10 kilowatts is a certain number of kilowatt hours. And that is what you produce, and that is what you see here at this column. So, and that is what you do for each and every column, and that if you add up all of them, you get the annual energy yield. Yeah, okay, this is how we're already through with this. I think, well, probably the most important information for you is if you have to control a generator and a wind turbine, make sure that you have proper safety systems installed. Even if you build a wind turbine for low wind sites, sooner or later there will be a gust or a storm which destroys your wind turbine if you don't calculate it correctly according to the wind class you design it for. And if you don't set up a wind, like a safety system, like a stalling system, and usually it is the best idea to combine an aerodynamic brake with a generator brake as one system. So that is very cost effective because you just need to monitor the power output, and when you get close to the maximum, just decrease the rotational speed, you get a stall effect, and the rotor automatically decreases the power output. So that is one brake, which can be done by, if you say you do microcontroller systems, then that should be quite easy. The second brake could be either an active aerodynamic brake by turning the blades, or it could be a mechanic brake, which is usually very difficult to realize because you need some backup power to activate the brake or to keep it locked. We usually recommend not to use this mechanic brake because that creates problems only in small wind turbines. In large wind turbines it can be done, but in small wind turbines we do not recommend it. Another very famous version for small wind turbines is simply furling, turning the rotor out of the wind. Yeah. And that could be done either with an electromechanic approach, like measuring the wind direction and actively turning the rotor out of the wind with a motor, yawing motor, or alternatively with a pure aerodynamic mechanic approach with a slight eccentric force introduction of the rotor thrust into the generator. Like the generator is not in the middle of the tower, but is slightly eccentric, and the higher the wind speed and the more power. Now let's say the power taken from the wind is linear to the rotor thrust, approximately linear to the rotor thrust. So the more power you take, the more force will be generated, and then the rotor will automatically turn out of the wind. The higher the power you take, you retrieve from the wind speed. And that is usually systems with wind vanes at the end. So that would be an option which is suitable for turbines up to 10 kilowatts. I wouldn't go for, like if you have larger turbines, 20, 30 or 100 kilowatts, I wouldn't go for the wind vane anymore. What is the size you're working on right now? You're not working on that yet? Okay.
sometimes in the telco company, they put the small wind turbine at the tower, and they said that there is any frequency from the wind to the
Right, it is.
communication. Is it true?
Yeah, it is true.
Yeah.
And the wind turbines emit a whole range of frequency. First is, of course, the rotational speed of the rotor. Like if you have 60 RPM, it's 60 RPM, right? Which are introduced into the tower. Second is 3 times, like if you have a 3-bladed machine, like turbine, you've got 3 times the rotational speed, because whenever the blade crosses the tower, you've got a shading effect. Like the tower, in front of the tower, the wind speed is not as high as behind, or as left or right of it. So 3 times the rotational speed, you've got a frequency. So that is the second one. That is the worst. You have to take care of that one the most, because the amplitude is the highest. The third frequency you will see is the generator frequency, or if you've got a gearbox frequency, which is just the pole pairs into the rotational speed. Now, if you've got a wind turbine which runs with a fixed rotational speed, you can calculate those frequencies quite exactly. But as we've seen, it makes more sense to have a variable rotational speed machine to track the maximum efficiency for each wind speed. And well, if you do that, you've got all the different ranges of frequencies. And one approach of how to solve this is to have a control which like lets the wind turbine run through resonance frequency of the towers, eigenfrequencies of the towers, very quickly, and and uses the rotation speed before and behind the eigenfrequency. So that would be a control system which could be developed by you, for example. Or by us. So this is something that we do, for example. But it's still very difficult to put these turbines on top of towers, especially if it's larger turbines. What I've seen quite often is turbines of 1 kilowatt, 1.5 kilowatt on top of towers. If you go to 5 kilowatts, 10 kilowatts, you usually have separate towers, because the frequency is too much.
And the second question is regarding before we want to know the potential of wind turbine. Actually, how long we can collect the data? Sometimes they said 10 years or 20 years data.
No, well,
On the collection, so this is potential or not. That's then when we want to install, it means that when we start here today, so you can install maybe the 20.
All right. Now there are several levels of data evaluation. If you want to have it very, very correct, you measure for several years, 10 years, whatever. But that is usually not required, because there are some weather stations which have the comparison between the different years. It doesn't even make too much difference if you measure at 10 meters, 20, 30, 50 meters height. If you've got a weather station measuring at 10 meters height for 10 years or something, and there are probably some at airports or whatever sites, you could use that data just to compare the years. For you, it's just very important. If you want to set up a large wind turbine, you measure for a whole year to cover all different seasons, seasonal changes. Although I do not know how much, how many changes you have throughout the year. Is it really much? It's quite constant, isn't it?
It depends on the location.
Yeah, of course. Indonesia is huge. Right. Okay. Yeah, right. And then you take your whole year of measurements and you evaluate that according to the long-term data from the weather station. So and then you can say, okay, the year, like the year we have measured, compared to the other 9 years that the weather station measured, was lower or was higher. So we have to use a correction factor. So that would be one. So, but if you go for smaller wind turbines of, let's say, below 100 kilowatts or below 500 kilowatts, people usually do not like to measure a whole year. And therefore, like for example, these small wind monitoring towers, we usually recommend to set them up for 3 months. Then you have got 3 months of data, and then we take the data of a weather station, which covers at least 1 year. And then we've got an algorithm. I'll tell you how it works. If you've got the time series, like 10 minutes averages, for example, of your reference data from the weather station and your own data, measured on site exactly where the wind turbine is supposed to be installed. You match the different time slots, like put them directly next to each other, and you've got wind direction and wind speed for both of them. And whenever the wind direction is like plus minus 15 degrees similar of both sides, you can say, okay, for this wind direction, the wind speed has got a factor of this. Like the factor between the two wind speeds is like this. And therefore this is how we evaluate or derive a factor for each wind direction. We do that because we want to get the local wind shading of obstacles in the vicinity out of the equation. And therefore we need factors for each wind direction. And then we use these factors and multiply the long time series with this factor. If we want to make it more sophisticated, you can still take into consideration the v to the power 3 behavior. Yeah, so that would even be a little bit more sophisticated. And if you want to make it even more sophisticated, then you can compare this result with the long-term average over the 10 years and have a correction factor then. So but with this method of measuring 3 months and extrapolating to a whole year and then derivating the energy yield from that, we have an energy yield estimation of plus minus 20% approximately, which is for small wind turbine usually good enough. If you want to have it more exact, then of course you have to measure.
The 3 months is, for example, January, February, March, or we can.
You can just pick any month, any 3 months out of the year. Yeah. Yeah, and especially for those telecom people, yeah, they wouldn't even wait for 3 months. Yeah. Yeah. So if you tell them, okay, but at least measure for 1 month, and they do it, then you probably can get a value which indicates, okay, at this site it makes sense or it doesn't make sense, like that. What was that roughly what you expected, what you wanted to know?
Yeah, for me that's enough. Very, I don't know. Can we get this file or not?
The wind file.
We have already actually.
Yeah.
No. Similar presentations.
Okay. I think I chose quite an old version of this. I have a little bit more updated one.